When you look up at the night sky, you see thousands of stars scattered across the darkness. But here is something that might change how you think about that view. Almost every single star visible to your naked eye belongs to just one galaxy. Our galaxy, the Milky Way. And the Milky Way is just one member of a much larger family, a collection of approximately 50 galaxies that astronomers call the local group. This is not a story about distant cosmic structures billions of light years away. This is about our neighborhood. These galaxies are close enough that we can study them in detail, close enough that their gravity affects us, and close enough that some will eventually collide with us. The local group stretches across roughly 10 million light years. A light year is the distance light travels in 1 year, moving at 186,000 miles per second. In 1 year, light covers about 5.8 trillion miles. So, 10 million light years equals 58 octillion, 800 quadrillion miles. Here is a better way to think about scale. If you could shrink the entire observable universe down to the size of Earth, the local group would be about the size of a small house. We are talking about a tiny pocket in the cosmic ocean. 3 massive spiral galaxies dominate this pocket. First, our own Milky Way, home to somewhere between 100 billion and 400 billion stars, along with their planets, moons, asteroids, comets, and vast clouds of gas and dust. The Milky Way is a barred spiral galaxy with a central bar-shaped structure and spiral arms extending outward. Our Sun sits about 26,000 light-years from the galactic center in a spiral arm called the Orion Spur. Think of the Milky Way like a cosmic city. The center is downtown, densely packed with stars. Out in the spiral arms where we live, things spread out more. The whole structure spans about 100,000 light-years across and only about 1,000 light-years thick in the disk. If you scaled it down to the size of a dinner plate, it would be thinner than a sheet of paper. The Milky Way formed about 13.6 billion years ago, not long after the Big Bang. Over those eons, it has grown by consuming smaller galaxies. This is not a metaphor. Large galaxies literally devour smaller ones, tearing them apart with gravity and absorbing their stars. Then there is Andromeda, also called Messier 31, the largest galaxy in our neighborhood. Andromeda sits about 2.5 million light-years away. On cosmic scales, Andromeda is practically on our doorstep. It is so close that it appears in our sky as a faint smudge visible to the naked eye on a dark, clear night. You are looking at light that left that galaxy 2.5 million years ago, when our ancestors were just beginning to use stone tools. Andromeda contains roughly 1 trillion stars, making it about 2.5 times more massive than the Milky Way. The disk of Andromeda stretches about 220,000 light-years across, more than twice the diameter of the Milky Way. Like the Milky Way, Andromeda is a barred spiral galaxy, though its bar is harder to see than ours. It has a supermassive black hole at its center, weighing in at about 110 million to 230 million times the mass of our Sun. Finally, there is Triangulum, Messier 33, sitting about 3 million light-years from the Milky Way. Triangulum is the 3rd largest galaxy in the local group, and the smallest of the 3 main spirals. Unlike the Milky Way and Andromeda, which both have bars at their centers, Triangulum is a pure spiral galaxy. Its spiral arms emerge directly from the central core without any intervening bar structure. Triangulum contains about 40 billion stars and measures roughly 60,000 light-years across. What Triangulum lacks in size, it makes up for in beauty. It is one of the most photogenic galaxies in the sky, with well-defined spiral arms and bright regions of star formation scattered throughout its disk. Triangulum is actively forming new stars much more vigorously relative to its mass than either the Milky Way or Andromeda. Orbiting around these three giants, scattered throughout the space between them, are dozens of smaller galaxies. Most are what astronomers call dwarf galaxies. Understanding these small systems is crucial because they outnumber large galaxies by vast margins and reveal fundamental truths about how galaxies form and evolve. Dwarf galaxies come in several varieties. Dwarf elliptical galaxies have a smooth, rounded appearance with no distinct structure. Dwarf spheroidal galaxies are similar, but even less structured, often appearing almost formless. Dwarf irregular galaxies have chaotic shapes and are typically still forming stars. Each type tells a different story about galaxy evolution. The key characteristic that unites all dwarf galaxies is their dominance by dark matter. Dark matter is the invisible substance that makes up about 85% of all matter in the universe. We cannot see it because it does not emit, absorb, or reflect light, but we know it exists because we can see its gravitational effects. When astronomers measure how fast stars move in dwarf galaxies, they find the stars are moving too fast to be held together by the gravity of the visible matter alone. There must be additional mass, present dark matter. The ratios are staggering. In typical dwarf spheroidal galaxies, dark matter outweighs visible matter by factors of hundreds to one. In the most extreme cases, like some ultra-faint dwarfs, the ratio reaches 3,000 to 1. These galaxies are essentially clouds of dark matter with a thin sprinkling of stars on top. This extreme dark matter dominance makes them ideal laboratories for studying this mysterious substance. Scientists point gamma-ray telescopes at these galaxies, searching for radiation that might be produced if dark matter particles occasionally collide and annihilate. So far, no definitive signals have been found, but the search continues. Most dwarf spheroidal galaxies are ancient, having formed more than 10 billion years ago. They stopped forming new stars long ago in many cases, over 10 billion years ago. They are filled with ancient reddish stars, but you will not find many young blue stars there. Something shut down their star formation. The leading theories involve several mechanisms working together. First, these small galaxies have shallow gravitational wells, meaning their gravity is relatively weak. When the first generation of massive stars formed and exploded as supernovae, the energy from those explosions may have been enough to blow away the remaining gas, removing the raw material needed for future star formation. Second, radiation from the early universe may have heated the gas in these small galaxies too much for it to collapse and form new stars. This process, called reionization, happened in the first billion years after the Big Bang, when the first stars and galaxies formed and filled the universe with ultraviolet radiation. Third, environmental effects play a role. When a dwarf galaxy orbits close to a larger galaxy, like the Milky Way or Andromeda, several things happen. Tidal forces can strip stars away. Ram pressure from hot gas in the larger galaxy's halo can strip away cold gas clouds. Radiation from the larger galaxy can heat and ionize gas, preventing it from forming stars. The result is that most dwarf spheroidals are dead galaxies, fossils from the early universe, and that makes them incredibly valuable to astronomers. Because their stars are so old, they formed when the universe was very young and had a different chemical composition. By studying the chemical elements in these stars, Astronomers can learn about conditions in the early universe and trace the history of element production from the pure hydrogen and helium of the Big Bang to the rich mix of elements we see today. The Milky Way has somewhere between 50 and 60 satellite galaxies that we know of. The most famous are the Large Magellanic Cloud and the Small Magellanic Cloud. If you live in the southern hemisphere, you can see both with your naked eye. They look like detached pieces of the Milky Way, two fuzzy patches of light. The Large Magellanic Cloud sits about 160,000 light-years away and contains roughly 30 billion stars, measuring about 14,000 light-years across. The Small Magellanic Cloud is a bit farther, about 200,000 light-years distant, and smaller, with maybe 3 billion stars. Both are irregular in shape and actively forming new stars at a high rate. For a long time, astronomers thought the Magellanic Clouds were permanently bound to the Milky Way. But more recent observations suggest they might be on their first pass by our galaxy, just stopping by for a visit. And that visit might not end well for them. The Milky Way's gravity is already distorting both clouds, pulling streams of gas away from them. Eventually, they will probably be torn apart completely and absorbed. The Sagittarius Dwarf Elliptical Galaxy is particularly interesting because it is currently being destroyed by the Milky Way. It sits on the opposite side of our galaxy from us, about 70,000 light-years from the galactic center. The Sagittarius Dwarf has already made several passes through the Milky Way's disk. Each time, our galaxy's gravity pulls stars away from it. These stolen stars form long streams that wrap around the Milky Way multiple times, creating a complex web. When the Sagittarius Dwarf passes through the Milky Way's disk, it does more than just lose stars. The collision sends ripples through our disk, like a pebble dropped in a pond. These ripples can trigger star formation and might even affect the orbits of stars near the Sun. Some scientists think the Sagittarius Dwarf passed through the disk about 300 million years ago, possibly disturbing the solar system's orbit around the galactic center. Over the next few billion years, the Sagittarius Dwarf will continue to lose stars until it is completely torn apart. Its stars will become indistinguishable from the rest of the Milky Way's stellar population. The only evidence it ever existed will be the chemical signatures of its stars. The Fornax Dwarf Spheroidal Galaxy sits about 460,000 light-years from the Milky Way. What makes Fornax remarkable is its collection of 6 globular clusters. Globular clusters are dense balls of stars, typically containing hundreds of thousands to millions of stars packed into a region only a few dozen light-years across. They are some of the oldest objects in the universe, with ages of 10 to 13 billion years. For a galaxy of Fornax's size and mass, 6 globular clusters is unusual. Most dwarf spheroidals have 0 or maybe 1. This tells us that Fornax was once much more massive. Imagine Fornax 10 billion years ago, perhaps 10 times its current mass, with enough gravity to form and retain these massive clusters. Then, over eons, as Fornax orbited the Milky Way, tidal forces slowly stripped away its outer layers. The globular clusters, being dense and compact, survived. They are like fossils, evidence of a much larger galaxy that existed in the distant past. The Sculptor Dwarf Spheroidal sits about 290,000 light-years away. Discovered in 1937 by Harlow Shapley, Sculptor contains only a few million stars, all of them old. There has been no star formation in Sculptor for at least 10 billion years. What Sculptor lacks in star formation, it makes up for in scientific value. Its ancient stars preserve information about the early universe's chemical composition. Andromeda has at least 35 satellite galaxies. The most prominent are M32 and M110. M32 is a compact, elliptical galaxy sitting right next to Andromeda, only about 22,000 light-years from Andromeda's center. M32 contains several billion stars packed into a very small volume. It is one of the densest galaxies known, with stars much closer together than in typical galaxies. The compact nature of M32 suggests it might be the stripped core of what was once a much larger spiral galaxy. Billions of years ago, this larger galaxy may have come too close to Andromeda. Andromeda's gravity tore away the outer parts, stripping away its spiral arms, disk, and halo. What remained was just the dense central core. NGC 147 is a dwarf spheroidal galaxy about 2.7 million light-years from the Milky Way. NGC 147 is interesting because it seems to be in the process of falling into Andromeda. Its orbit is decaying. Each time it passes Andromeda, it loses energy. Its orbit becomes smaller. Eventually, perhaps in a few billion years, NGC 147 will fall into Andromeda and be torn apart. Beyond the satellites of the Big Three, the local group contains several isolated members floating in the space between the major systems. IC10 is a dwarf irregular galaxy, about 2.2 million light-years from the Milky Way, sitting roughly between us and Andromeda. IC10 is forming stars very actively. It has one of the highest star formation rates per unit mass of any galaxy in the local group. IC 1613 is another dwarf irregular galaxy, located about 2.4 million light-years from the Milky Way. It appears to be interacting with intergalactic gas clouds, which might be triggering its star formation. Sextans A and Sextans B are both dwarf irregular galaxies located about 4 to 5 million light-years from the Milky Way, at the outer edges of the local group. Both are forming new stars, though not as vigorously as IC10. Sextans A has a very elongated shape, suggesting it might have been disturbed by a gravitational interaction in the past. Then there are the ultra-faint dwarf galaxies, discovered only in the late 20th or early 21st century. These include galaxies like Segway 1, Segway 2, Willman 1, Boots 1, and Boots 2. These ultra-faint dwarfs are at the absolute lower limit of what we can call a galaxy. Some contain only a few thousand stars. Segway 1, discovered in 2006, is located about 75,000 light-years from the Milky Way and contains only about 1,000 stars. When Segway 1 was first discovered, there was debate about whether it was actually a dwarf galaxy or just a globular cluster. The key difference is that dwarf galaxies have dark matter, while globular clusters do not. By measuring the velocities of stars in Segway 1, astronomers determined that the stars were moving too fast to be held together by visible matter alone. This confirmed Segway 1 is indeed a galaxy. What makes Segway 1 extraordinary is its dark matter ratio of about 3,000 to 1. It is essentially a cloud of dark matter with a tiny sprinkling of stars. Willman 1 is even smaller, with only a few hundred stars orbiting the Milky Way at a distance of about 120,000 light-years. These ultra-faint dwarfs might be the most common type of galaxy in the universe. For every large galaxy like the Milky Way or Andromeda, there might be hundreds or thousands of these tiny galaxies scattered around. We just cannot see most of them because they are too far away and too faint. Moreover, these ultra-faint dwarfs are incredibly old. They seem to have formed their stars in a single burst more than 13 billion years ago, shortly after the Big Bang, and then stopped. This makes them fossils from the early universe. They formed from gas that was enriched by only a few of the first supernovae, so they have very low abundances of heavy elements. By measuring exactly how much of each element is present, astronomers can infer what the first stars were like and how they enriched the early universe. For most of human history, we did not know that galaxies existed. When people looked at fuzzy patches of light in the sky, they called them nebulae, thinking they were just clouds of glowing gas within our own Milky Way. The breakthrough came in 1923, when Edwin Hubble used the Hooker telescope on Mount Wilson in California to observe the Andromeda Nebula. Hubble resolved individual stars in Andromeda, and among those stars he found Cepheid variables. These are stars that pulsate regularly, getting brighter and dimmer in a predictable pattern. There is a relationship between how fast they pulsate and how bright they actually are. By measuring the pulsation rate, you can calculate true brightness. Comparing true brightness to apparent brightness gives you the distance. When Hubble did this calculation for Cepheids in Andromeda, he got a shocking result. Andromeda was about 900,000 light-years away, later revised to about 2.5 million light-years. Andromeda was far too distant to be part of the Milky Way. It had to be a separate galaxy. This discovery fundamentally changed our understanding of the cosmos. The universe was not just our Milky Way with some nebulae scattered around. It was a vast expanse filled with countless galaxies. In 1936, Edwin Hubble published a paper describing 12 galaxies that he considered part of the local system. This included the Milky Way, Andromeda, Triangulum, the Magellanic Clouds, and a handful of dwarf galaxies. Over time, as telescopes improved and survey techniques became more sophisticated, more members were added. By the middle of the 20th century, astronomers knew of about 24 local group galaxies. By the end of the century, that number had grown to about 40. Today, we know of approximately 50 to 60 confirmed members. Finding these galaxies, especially the fainter ones, requires painstaking work. Astronomers use wide-field telescopes to photograph large areas of the sky. They then use computer algorithms to search these photographs for slight concentrations of stars that might indicate a dwarf galaxy. Once a candidate is identified, astronomers must confirm it is actually a galaxy and not just a random clump of stars, and that it is actually part of the local group and not some more distant object. This work continues today with large ground-based surveys. The Sloan Digital Sky Survey revolutionized the field in the early 2000s by photographing huge swathes of the sky and creating massive databases that could be searched for new discoveries. The Dark Energy Survey continued this work. The upcoming Legacy Survey of Space and Time, to be conducted by the Vera C. Rubin Observatory, will photograph the entire visible sky repeatedly. Based on current predictions, the Rubin Observatory might discover dozens of new ultra-faint dwarf galaxies in the local group over the next decade. The Hubble Space Telescope's program to observe Cepheid variables in nearby galaxies continues today, helping build up a three-dimensional map of the local group. The Gaia mission, a European Space Agency satellite, is measuring the positions and velocities of billions of stars in the Milky Way. By tracking how stars move over time, Gaia reconstructs their orbits and reveals the structure and dynamics of our galaxy. Gaia has also observed stars in some of the nearer dwarf galaxies, helping to measure their internal motions and map their dark matter distributions. Radio telescopes map hydrogen gas distribution in galaxies by detecting 21-centimeter radio waves. This reveals the raw material for future star formation and how gas is moving. The Atacama Large Millimeter Array, or ALMA, observes cold gas and dust in galaxies, the material just beginning to collapse to form new stars. The James Webb Space Telescope, which launched in 2021, is adding its capabilities with its ability to see in infrared light, penetrating through dust clouds to reveal hidden star-forming regions and ancient stars. Ground-based telescopes are also becoming more powerful. Adaptive optics systems correct for the blurring effects of Earth's atmosphere, allowing ground-based telescopes to achieve resolution almost as sharp as space telescopes. Gravitational wave detectors like LIGO and Virgo can detect ripples in spacetime produced by colliding black holes and neutron stars. Neutrino detectors catch elusive particles produced in supernova explosions. All of these different types of observations combine to create a rich, detailed picture of the local group. In 2020, astronomers using data from Gaia discovered that a stream of stars in the Milky Way's halo, called the Gaia Enceladus stream, is the remnant of a large dwarf galaxy that collided with the Milky Way about 10 billion years ago. This galaxy, nicknamed Gaia Enceladus or the Gaia Sausage, was quite substantial, containing several billion stars. When it collided with the Milky Way, it was torn apart, and its stars were scattered throughout the Milky Way's halo. This discovery was surprising because it showed that the Milky Way had a major merger relatively recently in its history. Before this, astronomers thought the Milky Way had been relatively calm, growing mainly by consuming small dwarf galaxies. Studies of Andromeda have revealed that it too has had major mergers in its past. Andromeda's halo contains streams and shells of stars, the remnants of dwarf galaxies it has consumed. One of the most interesting features is a giant stream of stars called the Great Southern Stream. This stream stretches for hundreds of thousands of light years. It is thought to be the remnant of a dwarf galaxy that collided with Andromeda several billion years ago. These tidal streams are like archaeological sites. They preserve information about the galaxies that were destroyed to create them. By measuring the positions and velocities of stars in a stream, astronomers can reconstruct the orbit of the original galaxy and learn about its mass and structure. The most important force at play in the local group is gravity. Gravity operates on multiple scales simultaneously. On the largest scale, there is the gravity of the entire local group, pulling all galaxies toward the center of mass of the system. This center of mass lies somewhere between the Milky Way and Andromeda, closer to Andromeda because it is more massive. Then there is the gravity of individual large galaxies. These galaxies have gravitational fields that extend far beyond their visible disks. These fields capture smaller galaxies and hold them in orbit. On an even smaller scale, gravity within individual galaxies holds stars in their orbits around the galactic center. When astronomers measured how far stars orbit in galaxies, they found something unexpected. Stars far from the galactic center were moving much faster than they should be based on the amount of visible matter in the galaxy. According to Newton's laws of gravity, stars far from the center should be moving more slowly. The fact that stars in the outer parts of galaxies move faster than expected means there must be more mass than we can see dark matter. Dark matter is distributed in roughly spherical halos that extend far beyond the visible disk of galaxies. The Milky Way's dark matter halo extends at least several 100,000 light-years from the center, possibly even farther. Andromeda's halo is similar. These halos overlap in the space between our galaxies. The total mass of the Milky Way, including its dark matter halo, is about 1.5 trillion times the mass of the Sun. Only about 10% of that is visible matter. Understanding dark matter is one of the biggest challenges in modern physics. We know it exists because we can see its gravitational effects, but we do not know what it is made of. It does not emit, absorb, or reflect light. It only interacts through gravity and possibly through the weak nuclear force. Scientists have proposed many candidates for what dark matter might be. The most popular is a hypothetical particle called a WIMP, which stands for Weakly Interacting Massive Particle. WIMPs would be heavier than protons, but would interact only weakly with normal matter. Experiments around the world are searching for WIMPs, trying to detect the rare occasions when a WIMP might collide with a normal atom. Another possibility is that dark matter consists of axions, extremely light particles. Or dark matter might be primordial black holes formed in the early universe, rather than from collapsing stars. Radiation pressure also plays a role, though a much smaller one than gravity. Stars emit light, and light carries momentum. When light from a star hits a cloud of gas or dust, it can push on that gas or dust. For most purposes in galaxy dynamics, radiation pressure is negligible compared to gravity. But in certain situations, it can be important. In regions where massive stars are forming, intense radiation can push on surrounding gas clouds. This radiation pressure can compress the gas, triggering even more star formation. It can also blow gas out of a galaxy entirely if the radiation is intense enough. This is thought to be one of the mechanisms that shuts down star formation in dwarf galaxies. The first generation of massive stars forms, and their radiation blows away the remaining gas, preventing future generations of stars from forming. Galaxies also have magnetic fields threading through them, created by the motion of charged particles in the gas and plasma that fills the galaxy. These magnetic fields can affect the motion of gas clouds and can influence star formation. The strength of magnetic fields in galaxies is tiny compared to the strength of gravity, but they can still have important effects on small scales. For instance, magnetic fields can provide support against gravitational collapse in a gas cloud, making it harder for the cloud to collapse and form stars. This can regulate the rate of star formation. Some dwarf galaxies show signs of tidal disturbances. Their shapes are elongated or asymmetric, suggesting they have been stretched by the gravity of a larger galaxy. Streams of stars extend from some dwarfs, marking where stars have been pulled away. These tidal streams can persist for eons, slowly dispersing as individual stars drift apart. Dwarf galaxies can also interact with each other. When two dwarfs pass close together, their mutual gravity can perturb their orbits and trigger star formation. We see evidence of this in some irregular dwarf galaxies, which have bursts of recent star formation that might have been triggered by close encounters. The gas in and around local group galaxies also interacts. Galaxies contain vast amounts of gas, some within the galaxies themselves and some in the space between galaxies. This intergalactic gas can be pulled from one galaxy to another by gravity. It can be heated by shock waves from supernova explosions. It can be ionized by radiation from hot young stars. One particularly interesting interaction involves ram pressure stripping. When a dwarf galaxy moves through the hot diffuse gas that fills the space between galaxies, the pressure of that gas can strip away the cold gas from the dwarf galaxy. This removes the raw material for star formation, effectively shutting down the galaxy's ability to make new stars. This might be part of the reason why many dwarf spheroidals stopped forming stars eons ago. The local group is not isolated. It sits near the edge of a much larger structure called the Virgo supercluster, also known as the Laniakea supercluster. This is a vast concentration of galaxy groups and galaxy clusters spanning about 520 million light-years. The local group is being pulled toward the center of this supercluster by the collective gravity of all those galaxies. We are moving through space at about 1.3 million miles per hour, relative to the cosmic microwave background radiation, and much of that motion is due to this gravitational attraction. The local group is falling toward an especially dense region of the Virgo supercluster called the Great Attractor. This is a gravitational anomaly, a region where the density of matter is much higher than average. The Great Attractor is pulling not just the local group, but hundreds of other galaxy groups and clusters toward it. Beyond the Great Attractor, there is an even larger concentration of galaxies called the Shapley supercluster, also exerting a gravitational pull on us. One way to think about the local group is as a hierarchy of structures. At the top level, you have the group as a whole, a collection of galaxies spanning 10 million light-years. At the next level down, you have subgroups centered on the Milky Way and Andromeda. Each contains one large galaxy surrounded by dozens of smaller satellites. At an even finer level, you have individual galaxies, each containing billions of stars organized into disks, bulges, and halos. And at the finest level, you have stellar systems, individual stars and their planets, moons, asteroids, and comets. Each level has its own characteristic timescales and physical processes. At the level of individual stars, things happen relatively quickly. Stars form, evolve, and die over millions to billions of years. Planets orbit their stars over years to decades. At the level of galaxies, things happen more slowly. It takes hundreds of millions of years for a star to complete one orbit around the galactic center. At the level of the local group, things happen even more slowly. This hierarchy is a fundamental feature of the universe. It exists because gravity is a long-range force that can act over vast distances, and also because matter tends to clump together under its influence. Start with a nearly uniform distribution of matter. Add gravity and time, and you get hierarchical structure. On the smallest scales, matter clumps into stars and planets. On larger scales, stars clump into galaxies. On even larger scales, galaxies clump into groups and clusters. And on the largest scales, groups and clusters clump into superclusters and filaments. The local group is one node in this vast cosmic web, connected to other groups and clusters through tendrils of dark matter and galaxies. Modern cosmological simulations are incredibly sophisticated. They include not just gravity and dark matter, but also the physics of gas, star formation, feedback from supernovae and stellar winds, radiation from stars, magnetic fields, and cosmic rays. They run on some of the most powerful supercomputers in the world and can track billions of particles as they evolve over cosmic time. By running these simulations and comparing the results to what we observe, astronomers test whether their theoretical models are correct. If the simulations produce galaxies that look like the ones we see, with similar sizes, structures, and properties, then the models are probably on the right track. One of the great successes of this approach has been the development of the Lambda CDM model of cosmology. This is our current best model of how the universe formed and evolved. Lambda refers to dark energy, the mysterious force causing the expansion of the universe to accelerate. CDM stands for cold dark matter, a particular type of dark matter that moves relatively slowly compared to the speed of light. The Lambda CDM model has been remarkably successful at explaining a wide range of observations, from the cosmic microwave background radiation to the large-scale structure of the universe to the properties of galaxies. But the model is not perfect. There are some observations that do not quite match the predictions. The missing satellites problem is one example. Computer simulations of how dark matter should behave predict that a large galaxy like the Milky Way should have hundreds or even thousands of small dark matter halos orbiting around it. Some of these halos should have stars in them, making them dwarf galaxies. But we only see a few dozen dwarf galaxies around the Milky Way. Where are all the others? There are several possible answers. Maybe many of the predicted dark matter halos are too small to form stars, so they are invisible to us. Maybe we have not found them yet because they are too faint. Maybe the simulations are wrong and there are not as many small halos as predicted. Or maybe our understanding of dark matter is incomplete. Another discrepancy is the core cusp problem, which has to do with the distribution of dark matter in the centers of dwarf galaxies. Simulations predict that dark matter should be very concentrated at the centers of galaxies, forming what is called a cusp. But observations suggest that the dark matter in dwarf galaxies is more evenly distributed, forming what is called a core. These discrepancies might indicate that our models are missing some important physics. Maybe star formation and supernova feedback are more effective at redistributing dark matter than the simulations account for. Maybe dark matter has properties we do not yet understand. Or maybe better observations will resolve the discrepancies. The major prediction of these simulations is the hierarchical model of galaxy formation. According to this model, galaxies form from the bottom up. Small structures form first, then merge to form larger structures, which merge to form even larger structures. The largest galaxies we see today are the result of countless mergers. We can see evidence of this hierarchical formation in the local group. The Milky Way and Andromeda both show signs of past mergers. The Milky Way has streams of stars wrapping around it, the remnants of dwarf galaxies it has consumed. Andromeda has a complex structure, with multiple stellar populations suggesting a turbulent merger history. We have known for about a century now that Andromeda is moving toward us. Or more accurately, we are moving toward each other. While most galaxies in the universe are moving away from us due to the expansion of space, Andromeda is one of the few galaxies that is actually getting closer. It is approaching at about 250,000 miles per hour. Current models suggest that about 4 billion years from now, the Milky Way and Andromeda will likely collide, though recent studies indicate there is some uncertainty about this. Perhaps a 50% chance it happens as predicted. If the collision does occur, it will be one of the most spectacular events in our cosmic neighborhood's history. The collision will not be like two rocks smashing together. Galaxies are mostly empty space. The stars are so far apart that even when two galaxies merge, individual stars almost never actually hit each other. Instead, the gravity of the two galaxies will tear each other apart and reshape each other. The spiral arms will be disrupted. Stars will be flung into new orbits. Clouds of gas will collide and trigger massive bursts of star formation. Over the course of a few billion years, the two galaxies will merge into a single, giant, elliptical galaxy that astronomers have already nicknamed Milkomeda or Milkdromeda. Triangulum might get pulled in too. Computer simulations suggest Triangulum could either collide with Andromeda before the Milky Way does, or it could be ejected from the local group entirely. During this merger, the supermassive black holes at the centers of both galaxies will also merge. This merger will release an enormous amount of energy in the form of gravitational waves, ripples in the fabric of space-time itself. What will happen to the smaller galaxies during this merger? Some will be thrown out of the system entirely, ejected into intergalactic space by the gravitational chaos. Others will be pulled in and absorbed, their stars added to the growing elliptical galaxy. A few might survive as satellites of the new merged galaxy, but they will be greatly diminished. But even further into the future, things get more interesting. The universe is expanding, and the rate of expansion is accelerating. This acceleration is caused by dark energy. Because of this expansion, distant galaxies are moving away from us. The farther away a galaxy is, the faster it is receding. There is a distance beyond which galaxies are receding from us faster than the speed of light. Not because they are moving through space faster than light, which is impossible, but because the space between us and them is expanding faster than light can traverse it. This means that light from those galaxies will never reach us. They are beyond what is called the cosmic event horizon. As the universe continues to expand and accelerate, this horizon will get closer. Galaxies that we can see today will eventually cross this horizon and disappear from view. The local group, bound together by its own gravity, will not expand with the universe. The Milky Way, Andromeda, and the other nearby galaxies are held together strongly enough that they will not be pulled apart by the expansion of space. But everything beyond the local group will slowly recede and eventually disappear. In about 150 billion years, the only galaxies visible from the merged Milky Way Andromeda system will be the remnants of the current local group. Every other galaxy will have receded beyond the cosmic event horizon. An astronomer living in that far future might look out at the universe and conclude that their galaxy is alone in the cosmos, with no evidence that any other galaxies ever existed. This means we live in a special time, a time when we can see the broader universe, when we can observe distant galaxies and learn about the large-scale structure of the cosmos. Future civilizations, if they exist, will not have that luxury. Eventually, in the very far future, trillions of years from now, even the stars will die out. Stars form from clouds of gas, and there is only a finite amount of gas in the universe. Once it is all used up, no new stars will form. The existing stars will slowly burn out. The most massive stars will die first, exploding as supernovae or collapsing into black holes. Medium-sized stars like our Sun will swell into red giants and then fade away as white dwarfs. The smallest stars, the red dwarfs, will be the last to go, but even they will eventually burn out. In 100 trillion years, the universe will be a very dark, very cold place. The merged galaxy, that was once the local group, will be filled with dead stellar remnants, white dwarfs, neutron stars, and black holes. There will be no light, no heat, no energy sources left except the slow evaporation of black holes via Hawking radiation. We do not know if there is life beyond Earth. We have not found any definitive evidence of it yet. But if life exists elsewhere, where might it be? Within our own Milky Way, there are hundreds of billions of stars, and we now know that most of those stars have planets. Some of those planets are in the habitable zone, the region around a star where temperatures are right for liquid water to exist on a planet's surface. Liquid water is considered essential for life as we know it. So, there are potentially billions of habitable planets in the Milky Way alone. If we extend this to the whole local group, the numbers become even more staggering. Andromeda has 1 trillion stars. Triangulum has 40 billion. Even the smaller galaxies have millions or billions of stars. If only a tiny fraction of those stars have habitable planets, and if only a tiny fraction of those habitable planets actually develop life, there could still be thousands or millions of living worlds in the local group. The key requirements for life as we know it are liquid water, a source of energy, and the right chemical building blocks. Water is common in the universe. Hydrogen and oxygen, the components of water, are the first and third most abundant elements in the universe. Anywhere you have the right temperature and pressure, water can exist in liquid form. Energy sources are also common. Stars provide energy through their light and heat. Chemical reactions can provide energy. Radioactive decay in a planet's interior can provide energy. The chemical building blocks of life, carbon, nitrogen, oxygen, phosphorus, and sulfur, are all produced in stars and spread throughout the universe when stars die. These elements are present in the gas clouds that form new stars and planets. So the ingredients for life are common. The question is whether they come together in the right way to actually produce life. On Earth, life arose relatively quickly after the planet formed. The Earth is about 4.5 billion years old, and we have evidence of life dating back at least 3.5 billion years. That means life arose in the first billion years of Earth's existence, possibly much sooner. If life arises readily whenever conditions are suitable, then there should be life throughout the local group. And if intelligent life does exist elsewhere, could we ever communicate with it? The distances are enormous. Even at the speed of light, it would take 2.5 million years for a message to reach Andromeda and another 2.5 million years for a reply to come back. But within our own Milky Way, the distances are more manageable. If there is intelligent life elsewhere in our galaxy, and if they have developed radio technology like we have, we might be able to detect their signals, or they might detect ours. This is the premise of the Search for Extraterrestrial Intelligence, or SETI. Radio telescopes scan the sky, looking for artificial signals that might indicate the presence of a technological civilization. There are also efforts to search for biosignatures, signs of life that might be detectable in the atmospheres of planets orbiting other stars. Oxygen, for example, is produced by photosynthetic life on Earth and is present in our atmosphere at levels that would not exist without life. If we could detect high levels of oxygen in the atmosphere of a planet orbiting another star, it would be strong evidence that life exists on that planet. The James Webb Space Telescope has the capability to analyze the atmospheres of planets orbiting nearby stars. While it cannot reach planets in other galaxies, it can study planets in our own Milky Way. Over the coming years, it will observe dozens of potentially habitable planets, looking for signs of water vapor, oxygen, methane, and other gases that might indicate the presence of life. If we do find evidence of life elsewhere, it would be one of the most profound discoveries in human history. It would answer one of the oldest questions we have asked: are we alone in the universe? But even if we never find life elsewhere, the search itself is valuable. It teaches us about the conditions necessary for life, about the diversity of planets and environments in the universe, about the chemical and physical processes that govern the cosmos. Studying the local group has taught us fundamental truths about how the universe works. First, we have learned that galaxies come in a huge range of sizes, from giants like Andromeda with 1 trillion stars to ultra-faint dwarfs with only a few thousand stars. This diversity tells us that galaxy formation is a complex process with many different possible outcomes depending on the initial conditions and the environment. Second, we have learned that galaxies are not isolated objects. They interact constantly. They collide and merge. They exchange gas. They pull stars away from each other. These interactions drive much of the evolution of galaxies over cosmic time. Third, we have learned that small galaxies are incredibly common but incredibly hard to find. The local group probably contains many more dwarf galaxies than we have discovered so far. By studying the orbits of satellite galaxies around the Milky Way, astronomers have been able to measure the total mass of the Milky Way, including its dark matter halo. By studying the star formation histories of dwarf galaxies, astronomers have learned about the conditions in the early universe. The oldest dwarf galaxies formed their stars when the universe was only a few 100 million years old. These first stars, called population 3 stars, were probably very massive, perhaps hundreds of times the mass of the Sun. They lived fast and died young, exploding as supernovae and seeding the universe with the first heavy elements. The next generation of stars incorporated these heavy elements into their makeup. By studying the chemical composition of stars in ultra-faint dwarfs, astronomers can learn about what those first population 3 stars were like. The local group teaches us about the cosmic web, the large-scale structure of the universe. The cosmic web is a network of filaments and sheets of galaxies separated by vast voids. The local group sits on a filament of this web, and the pull of that filament affects our motion through space. The local group also plays a crucial role in calibrating the cosmic distance ladder, the series of methods used to measure distances throughout the universe. We measure nearby star distances using parallax. These calibrate Cepheid variables. Cepheids calibrate distances to local group galaxies. These calibrate Type 1a supernovae, visible to much greater distances. This chain allows us to measure distances across the observable universe. The local group is also important for understanding reionization, which happened in the first billion years after the Big Bang. Initially, atoms in the universe were ionized. As the universe expanded and cooled, electrons recombined with nuclei to form neutral atoms. Then the first stars and galaxies formed, and their ultraviolet light reionized the hydrogen. Ultra-faint dwarf galaxies in the local group formed during or shortly after reionization, carrying information about the first generations of stars and galaxies. When we look at the galaxies in the local group, we are seeing objects that are millions of light years away. The light from Andromeda that reaches us tonight left that galaxy 2.5 million years ago. We are not seeing Andromeda as it is now, but as it was in the distant past. This illustrates that there is no such thing as a universal now that applies throughout the universe. The concept of simultaneity breaks down over cosmic distances. This is a consequence of Einstein's theory of relativity. The local group also illustrates the principle that the same physical laws apply everywhere in the universe. The stars in Andromeda follow the same laws of physics as the stars in the Milky Way. Gravity works the same way there as it does here. This universality of physical law is one of the foundational assumptions of science. The local group is fairly typical as galaxy groups go. It has a couple of large galaxies and many smaller ones, which is common. The Milky Way's position within the local group is not particularly unusual. This ordinariness is part of what is called the Copernican principle, the idea that we do not occupy a special or privileged position in the universe. The next few decades promise to be an exciting time for local group studies. New surveys will discover more members. New telescopes will observe known members in unprecedented detail. New simulations will model the formation and evolution of the local group with increasing realism. The Vera C. Rubin Observatory will survey the sky night after night, building up a massive database that can be mined for new discoveries. The extremely large telescope, currently under construction in Chile, will be able to resolve individual stars in galaxies throughout the local group. The Nancy Grace Roman Space Telescope will survey large areas of the sky in infrared light, revealing hidden populations of stars. Each of these facilities will contribute new pieces to the puzzle. And there is still so much to discover. Why do some dwarf galaxies have globular clusters while others do not? What determines whether a dwarf galaxy continues to form stars or shuts down? How much dark matter is there in the local group, and how is it distributed? Are there more ultra-faint dwarfs waiting to be discovered? What will the local group look like in 10 billion years after the Milky Way and Andromeda have merged? The local group is our window on the universe. It is where we learn about galaxy formation, dark matter, cosmic evolution, and our place in the grand scheme of things. Every discovery adds another piece to the puzzle. Every new telescope reveals more detail. Every simulation brings us closer to understanding how it all works. When you look at the night sky, most of what you see with your naked eyes is part of the Milky Way. But revealed by our telescopes are the other members of our cosmic community. The Magellanic Clouds in the southern sky, Andromeda as a faint smudge in the north, Triangulum, and dozens of dwarf galaxies, each one a tiny island of stars in the vast darkness of space. These galaxies are separated from us by distances that dwarf the space between stars, but they are still close enough that we can study them, close enough that their gravity affects us, close enough that our futures are connected. The approximately 50 galaxies of the local group are more than just astronomical objects. They are our cosmic context, the structure within which we exist. Understanding them means understanding ourselves, our origins, and our future in the cosmos. And that, in the end, is why we study the local group, not just because it is there, but because understanding it helps us understand ourselves and our place in the universe. To truly understand the local group, we need to understand what galaxies are made of and how they are structured. A galaxy is not just a random collection of stars. It is an organized system with distinct components, each with its own properties and history. Take the Milky Way as an example. At its center is the bulge, a roughly spherical concentration of old stars. The bulge contains about 10 billion stars packed into a region only a few thousand light-years across. The density of stars in the bulge is much higher than in the disk where we live. If you could somehow transport the solar system to the bulge, the night sky would be filled with thousands of stars brighter than Venus. Extending from the bulge is the disk, a flattened structure where most of the star formation happens. The disk contains most of the Milky Way's gas and young stars. It is organized into spiral arms, though the exact number and structure of these arms is still debated. The spiral arms are not permanent structures like the spokes of a wheel. They are density waves, regions where stars and gas are temporarily compressed as they orbit the galaxy. Think of it like a traffic jam on a highway. The cars move through the jam, but the jam itself stays in roughly the same place. Similarly, stars move through the spiral arms, but the arms themselves persist for hundreds of millions of years. The compression in the spiral arms triggers star formation, which is why the spiral arms appear bright in photographs of galaxies. Surrounding the disk and bulge is the halo, a roughly spherical region containing old stars, globular clusters, and very little gas. The halo extends far beyond the visible disk, perhaps as far as several 100,000 light-years. The stars in the halo are on highly eccentric orbits, plunging through the disk and then arcing far out into space before falling back down again. And surrounding everything is the dark matter halo, which extends even farther than the stellar halo. The dark matter halo is what holds the galaxy together. Without it, the galaxy would fly apart. The outer stars are moving so fast that the gravity of the visible matter alone could not hold them in orbit. Andromeda has a similar structure, though with some differences. Andromeda's bulge is larger and more massive than the Milky Way's. Its disk contains more stars, and its halo is populated with streams and shells of stars, evidence of past mergers. Triangulum, being smaller and having no bar, has a simpler structure. It has a small bulge, a thin disk with well-defined spiral arms and a less extensive halo. This simpler structure makes Triangulum an ideal laboratory for studying spiral galaxies without the complications introduced by bars and past mergers. Dwarf galaxies have much simpler structures. Dwarf spheroidals, for instance, have no disk at all. They are roughly spherical distributions of stars embedded in dark matter halos. Dwarf irregulars have some structure, with clumps of star formation scattered throughout, but nothing as organized as the spiral arms of large galaxies. Understanding these structures helps us understand how galaxies form and evolve. The disk formed from gas that fell into the galaxy and settled into a rotating plane. The bulge likely formed from a combination of stars that migrated inward from the disk and stars captured from smaller galaxies that merged with the Milky Way early in its history. The halo is populated mostly by stars from dwarf galaxies that were tidally disrupted and absorbed. One of the most powerful tools for understanding the history of galaxies is the chemistry of their stars. Stars are not all made of the same stuff. Some stars are almost pure hydrogen and helium. Others contain significant amounts of heavier elements like carbon, oxygen, iron, and gold. The reason for this difference is that the universe has been chemically enriched over time. When the universe was born in the Big Bang, it consisted of about 75% hydrogen and 25% helium, with just traces of lithium. That was it. There was no carbon, no oxygen, no iron, no silicon. None of the elements that make up planets or people or anything else existed. The first stars that formed, the population 3 stars, were made entirely of this pristine material. These stars were probably very massive, perhaps 50 to several hundred times the mass of our star. They burned brightly but briefly, perhaps only a few million years. When they exploded as supernovae, they scattered the first heavy elements into space. The next generation of stars, which we call population 2 stars, incorporated these heavy elements into their makeup. These stars still had low abundances of heavy elements, only about 1/10 to 1/100th the abundances we see in the Sun. But they were no longer pristine. Over time, as more and more stars formed, lived, and died, the abundance of heavy elements in the universe increased. The Sun, which formed about 4.5 billion years ago, has about 2% of its mass in elements heavier than helium. This might not sound like much, but it is crucial. Those heavy elements are what allowed planets to form and ultimately what allowed life to emerge. By measuring the abundances of different elements in stars, astronomers can determine when those stars formed. Stars with very low abundances of heavy elements must have formed early, when the universe was still relatively pristine. Stars with high abundances formed more recently, from gas that had been enriched by many generations of earlier stars. This is where the dwarf spheroidal galaxies come in. Many of their stars have extremely low abundances of heavy elements, indicating they formed very early in the universe's history. Some stars in ultra-faint dwarfs have iron abundances, only 1/10,000th that of the Sun. These stars are among the oldest in the universe, formed when the universe was only a few 100 million years old. But it is not just the total abundance of heavy elements that matters. The ratios of different elements also tell a story. For example, oxygen and magnesium are produced primarily in massive stars that explode as supernovae shortly after they form. Iron, on the other hand, is produced both in massive star supernovae and in a different type of supernova called a Type 1a supernova, which happens when a white dwarf accumulates too much mass from a companion star. Type 1a supernovae take longer to happen because it takes time for a white dwarf to accumulate enough mass. So in the early universe, before Type 1a supernovae started happening, the ratio of oxygen to iron was much higher than it is today. By measuring the oxygen to iron ratio in old stars, astronomers can determine when those stars formed relative to when Type 1a supernovae started happening. This helps reconstruct the early history of star formation in the galaxy. Different elements also tell us about different types of stellar processes. Elements like strontium, barium, and europium are produced in the rapid neutron capture process, or R process, which happens in neutron star mergers and certain types of supernovae. Elements like carbon and nitrogen are produced in lower mass stars during their later evolutionary stages. By measuring all these different elements, astronomers can piece together the full history of element production in a galaxy. The Milky Way's halo contains stars with a wide range of chemical compositions, reflecting the fact that the halo was built up from many different dwarf galaxies that were accreted over time. Each of these dwarf galaxies had its own chemical evolution history, and when they were disrupted, their stars preserved the chemical signatures of their parent galaxies. By analyzing the chemical compositions of halo stars, astronomers can identify groups of stars that likely came from the same parent galaxy, even though that galaxy was destroyed billions of years ago. They can piece together how many dwarf galaxies the Milky Way has accreted, when each accretion happened, and how massive each parent galaxy was. Galaxies are not static objects. Stars are constantly forming, evolving, and dying. Understanding the star formation history of a galaxy, when and how rapidly it formed stars over its lifetime, is crucial for understanding how the galaxy evolved. Star formation happens when clouds of gas and dust collapse under their own gravity. The gas heats up as it collapses, and eventually the temperature and pressure at the center become high enough for nuclear fusion to begin. A star is born. But star formation is a surprisingly inefficient process. Only about 1 to 2% of the gas in a molecular cloud actually ends up in stars. The rest is blown away by stellar winds and supernova explosions. Or it simply fails to collapse because of magnetic fields or turbulence in the gas. The rate at which a galaxy forms stars depends on how much gas it has and how efficiently that gas can collapse to form stars. Large spiral galaxies like the Milky Way and Andromeda have steady, ongoing star formation. They form several new solar masses worth of stars per year. This is a modest rate at this pace. It would take billions of years to convert all their gas into stars. Starburst galaxies, on the other hand, form stars at much higher rates, sometimes hundreds or thousands of solar masses per year. These bursts of star formation are typically triggered by galaxy mergers or close encounters, which compress the gas and trigger rapid star formation. The bursts do not last long, though perhaps only a few tens of millions of years because the intense star formation quickly exhausts the available gas. Dwarf irregular galaxies like IC10 have modest star formation rates in absolute terms, but relative to their mass, they are forming stars quite vigorously. They have enough gas to sustain star formation for billions of years at their current rates. Dwarf spheroidal galaxies, on the other hand, have no ongoing star formation. They stopped forming stars eons ago. Understanding why they stopped is one of the key questions in galaxy evolution. Astronomers study star formation histories by examining the populations of stars in a galaxy. Young stars are hot and blue, middle-aged stars like the Sun are yellow, old stars are cool and red. By measuring the numbers of stars of different colors and brightnesses, astronomers can reconstruct when those stars formed. This technique, called stellar population synthesis, reveals that different galaxies have very different star formation histories. Some galaxies formed most of their stars early and then stopped. Others have had steady star formation throughout their lives. Still others have had bursts of star formation separated by quiescent periods. The star formation history of a galaxy is intimately connected to its merger history. Major mergers trigger bursts of star formation. Minor mergers can bring in new gas that fuels star formation. Isolation can lead to gradual star formation as gas slowly settles into the disk. At the center of almost every large galaxy, including the Milky Way and Andromeda, lurks a supermassive black hole. These are not the stellar mass black holes that form when massive stars collapse. These are black holes with masses of millions to billions of times the mass of the Sun. The Milky Way's central black hole, called Sagittarius A star, has a mass of about 4 million times the mass of the Sun. We know it is there because we can see stars orbiting around it. These stars move incredibly fast. Some orbit at speeds of several percent the speed of light. By measuring the orbits of these stars, astronomers have determined the mass of the black hole and even measured effects predicted by Einstein's theory of general relativity. Andromeda's central black hole is more massive, perhaps 110 million to 230 million solar masses. Triangulum likely has a supermassive black hole too, though it is harder to detect because Triangulum is farther away and we cannot resolve individual stars near its center. How did these supermassive black holes form? This is still an open question. One possibility is that they formed from the first generation of stars in the early universe. If some of these first stars were massive enough, they might have collapsed directly into black holes without exploding as supernovae. These seed black holes could then have grown by accreting gas and by merging with other black holes. Another possibility is that they formed from the collapse of massive gas clouds in the early universe. If a cloud of gas with a mass of millions of solar masses could somehow collapse without fragmenting into stars, it could form a supermassive black hole directly. However they formed, supermassive black holes play an important role in galaxy evolution. When gas falls into a supermassive black hole, it heats up and emits enormous amounts of energy. This energy can blow away gas from the galaxy, shutting down star formation. This is called active galactic nucleus feedback, and it is thought to be one of the reasons why the most massive galaxies stopped forming stars. In the local group, the central black holes are relatively quiet. They are not accreting much gas, so they are not producing much energy. But this was not always the case. Evidence suggests that both the Milky Way's and Andromeda's black holes were more active in the past when there was more gas available for them to accrete. When the Milky Way and Andromeda merge, their central black holes will eventually merge too. This merger will release a tremendous amount of energy in the form of gravitational waves. Gravitational wave detectors like LIGO and Virgo are too small to detect such low-frequency gravitational waves. But future space-based detectors like LISA might be able to observe similar events in distant galaxies. Galaxies are not isolated islands of stars floating in empty space. They are surrounded by gas, and they are constantly exchanging gas with their surroundings. Understanding this gas cycle is crucial for understanding how galaxies evolve. The space between galaxies is not empty. It contains diffuse gas, mostly hydrogen, at very low densities. This intergalactic medium is generally very hot, heated to millions of degrees by shock waves from galaxy formation and by radiation from stars and black holes. Galaxies are constantly pulling in gas from the intergalactic medium. This process, called gas accretion, is essential for sustaining star formation. As a galaxy converts its gas into stars, it needs to replenish its gas reservoir. Without fresh gas coming in, star formation would gradually decline and eventually stop. Gas can accrete onto galaxies in two ways. In hot mode accretion, gas from the intergalactic medium falls into the galaxy's dark matter halo, where it is shock heated to millions of degrees. This hot gas slowly cools and settles onto the galaxy's disk, providing fuel for star formation. In cold mode accretion, gas streams along filaments in the cosmic web and falls directly onto the galaxy without being shock heated. This mode is thought to be more important in the early universe and in lower mass galaxies. Galaxies also lose gas. Stellar winds from massive stars blow gas out of the galaxy. Supernova explosions blast gas into space at high velocities. In small galaxies with shallow gravitational wells, this gas can escape entirely, leaving the galaxy with less gas available for future star formation. In larger galaxies, much of the gas blown out by stellar winds and supernovae eventually falls back onto the galaxy. This creates a galactic fountain, where gas is constantly cycling between the disk, the halo, and back to the disk. The intergalactic medium in the local group is very diffuse and hard to observe. But it is there, and it plays a role in the evolution of local group galaxies. Gas stripped from dwarf galaxies by tidal forces or ram pressure does not disappear. It joins the intergalactic medium, where it can eventually be accreted by larger galaxies. Galaxies are filled with more than just stars and gas. They also contain high-energy particles called cosmic rays and magnetic fields that thread through the gas and stars. Cosmic rays are charged particles, mostly protons, accelerated to nearly the speed of light. They are produced in supernova remnants, where the shock waves from the explosion accelerate particles to extreme energies. Cosmic rays permeate the galaxy, bouncing off magnetic fields and interacting with gas. When cosmic rays collide with gas atoms, they can produce gamma rays and neutrinos. They can also heat the gas and ionize it, affecting the rate of star formation. In some models, cosmic rays provide significant pressure support in the gas, helping to regulate how quickly gas collapses to form stars. Magnetic fields in galaxies are generated by the motion of charged particles in the gas and plasma. The rotation of the galaxy, combined with turbulence in the gas, creates a dynamo effect that amplifies weak seed magnetic fields over time. The magnetic fields we observe in galaxies today are the result of billions of years of this dynamo process. Magnetic fields affect how gas moves and collapses. They can provide support against gravitational collapse, making it harder for gas clouds to form stars. They can also channel gas flows, creating filaments and structures in the interstellar medium. Measuring magnetic fields in other galaxies is challenging. One technique is to observe polarized radio emission from the galaxies. Charged particles spiraling in magnetic fields emit radio waves with a preferred polarization direction. By mapping this polarization, astronomers can map the magnetic field structure. Another technique is to measure the Faraday rotation of background radio sources. As polarized radio waves pass through a magnetized plasma, their polarization direction rotates. The amount of rotation depends on the strength of the magnetic field and the density of the plasma. These observations show that galaxies like the Milky Way and Andromeda have large-scale magnetic fields with strengths of a few microgauss. This is about 1 million times weaker than Earth's magnetic field, but strong enough to affect the dynamics of the gas. One interesting feature of spiral galaxies is that they have metallicity gradients. Metallicity is astronomers' term for the abundance of elements heavier than helium. In spiral galaxies, the metallicity is highest in the center and decreases as you move outward through the disk. This gradient tells us about how the galaxy assembled. The current theory is that spiral galaxies grow from the inside out. The central regions formed first and have experienced many generations of star formation, building up high metallicities. The outer regions formed later and have had fewer generations of star formation, so their metallicities are lower. Gas that falls onto a galaxy typically has low metallicity because it has not been enriched by stellar processing. This gas preferentially falls onto the outer parts of the disk, diluting the metallicity there. Star formation in the outer disk is also less efficient, so there is less enrichment from local stellar evolution. The metallicity gradient in the Milky Way is fairly steep. The Sun, which sits about 26,000 light-years from the center, has a metallicity close to the average for stars at that distance. Stars closer to the center have higher metallicities. Stars farther out have lower metallicities. This gradient is not perfectly smooth, though. There are scatter and fluctuations reflecting the complex history of gas flows, stellar migration, and localized bursts of star formation. By mapping the metallicity gradient in detail, astronomers can constrain models of how the Milky Way assembled over time. Andromeda also has a metallicity gradient, though it is less well studied than the Milky Way's, because Andromeda is farther away and harder to observe in detail. Future observations with instruments like the James Webb Space Telescope will allow astronomers to map Andromeda's metallicity gradient more precisely. Dwarf galaxies generally do not have strong metallicity gradients because they are too small. Their gas is well mixed by turbulence and stellar feedback, homogenizing the metallicity throughout the galaxy. To truly understand the local group, we need to understand the context in which its galaxies formed. This takes us back to the early universe, to a time called the Epoch of Reionization. In the first few 100 million years after the Big Bang, the universe was dark. There were no stars, no galaxies, just clouds of hydrogen and helium gas slowly collapsing under gravity. This period is sometimes called the Cosmic Dark Ages, but eventually the first stars formed. These population 3 stars were massive and hot, producing copious amounts of ultraviolet radiation. This radiation ionized the hydrogen gas around the stars, creating bubbles of ionized gas. As more and more stars formed, these bubbles grew and eventually merged. By about 1 billion years after the Big Bang, the entire universe had been reionized. This epoch of reionization marks a major transition in the history of the universe. The ultra-faint dwarf galaxies in the local group are relics from this era. They formed their stars during or shortly after reionization and then stopped. Their stars preserve information about the conditions in the early universe when galaxies were just beginning to form. One key question is, what caused reionization? Was it the first massive stars in small proto-galaxies? Was it the first quasars, supermassive black holes accreting gas and producing enormous amounts of radiation? Current evidence suggests it was primarily the stars in early galaxies, but the exact contribution from different sources is still debated. Another question is, how did reionization affect galaxy formation? The ultraviolet radiation that reionized the universe also heated the gas, making it harder for small clumps of gas to collapse and form stars. This likely suppressed star formation in low-mass dark matter halos, which might explain why the ultra-faint dwarfs stopped forming stars so early. Studying the local group helps address these questions. By determining the star formation histories of ultra-faint dwarfs, astronomers can constrain when reionization happened and how it affected star formation in small galaxies. The local group is more than just a collection of galaxies. It is a laboratory for testing our theories of galaxy formation and evolution. Because it is so close, we can study local group galaxies in much more detail than we can study distant galaxies. For example, we can resolve individual stars in local group galaxies and measure their ages, compositions, and motions. This allows us to reconstruct the star formation histories of these galaxies with precision that is impossible for more distant galaxies. We can also study the dynamics of local group galaxies in detail. By measuring the velocities of stars and gas, we can map the distribution of dark matter and test theories about the nature of dark matter. We can search for tidal streams and shells of stars, the remnants of past mergers. These features are too faint to be detected in distant galaxies, but they are clearly visible in local group galaxies. We can study the gas content and star formation in local group galaxies. We can see individual star-forming regions and molecular clouds. We can measure the properties of the interstellar medium. All of this detailed information allows us to test our theories in ways that would be impossible if we only studied distant galaxies. When we develop a theory of galaxy formation, we can test it against the detailed observations we have of local group galaxies. If the theory does not match what we see in the local group, it probably does not work for the rest of the universe either. The local group also allows us to study environmental effects on galaxy evolution. We can compare satellites of the Milky Way to satellites of Andromeda to see if they evolve differently. We can compare isolated dwarfs to those in dense environments to see how environment affects star formation and gas content. These comparisons are possible because the local group contains a diverse sample of galaxies in different environments. It is a microcosm of the larger universe, and what we learn from it applies to galaxy groups throughout the cosmos. The study of the local group has been marked by several breakthrough observations that fundamentally changed our understanding. Each breakthrough was enabled by technological advances that allowed us to see things we had never seen before. One of the most significant was the discovery in the early 2000s of the ultra-faint dwarf galaxies. These galaxies are so faint that even though they are relatively nearby, they were completely invisible until digital sky surveys, like the Sloan Digital Sky Survey, came online. The discovery of these galaxies revealed a whole new population of objects that had been hiding in plain sight. The technique used to find them is ingenious. Astronomers take deep images of large areas of the sky. They then use sophisticated algorithms to identify slight overdensities of stars regions where there are slightly more stars than expected from random chance. These overdensities might indicate the presence of a dwarf galaxy. But not every overdensity is a galaxy. Some are just statistical fluctuations. Others are globular clusters or tidal streams. To confirm that an overdensity is actually a galaxy, Astronomers need to measure the velocities of individual stars. If the stars are all moving together with similar velocities, they are probably gravitationally bound and therefore form a galaxy. This requires spectroscopy of individual faint stars, which is technically challenging. But modern spectrographs on large telescopes can do this. They can measure velocities of stars as faint as magnitude 20 or 21, faint enough to pick out individual stars in ultra-faint dwarfs. Another breakthrough has been the ability to measure proper motions, the motion of stars across the sky, for stars in nearby dwarf galaxies. This was made possible by the Gaia mission, which has measured the positions of billions of stars with unprecedented precision. By comparing positions measured at different times, astronomers can determine how stars are moving across the sky. For nearby dwarf galaxies, this allows determination of their full three-dimensional motion, not just how fast they are moving toward or away from us, but also how fast they are moving across our line of sight. This information is crucial for understanding the orbits of satellite galaxies. It allows astronomers to calculate where a satellite galaxy has been and where it is going. It allows them to determine whether a satellite is on its first infold toward the Milky Way or whether it has made multiple passes. It helps constrain the mass of the Milky Way's dark matter halo. The measurement of chemical abundances in distant stars has also improved dramatically. Modern spectrographs can measure the abundances of dozens of different chemical elements in individual stars. This allows astronomers to reconstruct the detailed chemical evolution of galaxies and to identify stars that came from the same parent galaxy based on their chemical signatures. One technique that has proven particularly powerful is studying RR Lyrae variables. These are pulsating stars with well-known properties. They are old, they have a characteristic luminosity, and they pulsate with a period of about half a day. By finding RR Lyrae stars in a dwarf galaxy and measuring their properties, astronomers can determine the distance to the galaxy, its age, and its metallicity. The study of tidal streams has also benefited from technological advances. Streams are faint and extended, making them hard to detect. But by combining data from multiple sources, photometry from wide-field surveys, spectroscopy of individual stars, proper motions from Gaia astronomers can map streams in exquisite detail. They can determine which stars belong to the stream and which are foreground or background stars. They can measure how the stream's width, density, and velocity change along its length. They can use this information to model the orbit of the progenitor galaxy and to constrain the shape of the Milky Way's dark matter halo. Radio observations have revealed the distribution of neutral hydrogen gas in local group galaxies. Hydrogen emits radio waves at a wavelength of 21 centimeters, and radio telescopes can map this emission to see where the gas is located and how it is moving. These observations show that many dwarf galaxies have been stripped of their gas. The irregular dwarfs still have substantial gas reservoirs, but the spheroidal dwarfs have little to no detectable gas. This confirms the picture that environmental effects have removed gas from the spheroidal dwarfs, shutting down their star formation. The observations also reveal interesting structures in the gas. There are high-velocity clouds of hydrogen gas moving at velocities that do not match the rotation of the Milky Way's disk. Some of these clouds might be gas stripped from satellite galaxies. Others might be gas falling onto the Milky Way from the intergalactic medium. Infrared observations have revealed populations of old, cool stars in local group galaxies that would be invisible in optical light. The James Webb Space Telescope is now allowing astronomers to study these populations in unprecedented detail. It can see through dust clouds to reveal hidden star-forming regions. It can study the oldest stars in the local group, measuring their properties and testing theories of stellar evolution. Ultraviolet observations reveal the hottest, youngest stars in galaxies. These observations show where star formation is happening most vigorously. They can identify massive stars that will soon explode as supernovae, allowing astronomers to study these stars before they die. X-ray observations reveal the most energetic processes in galaxies. They can detect supernova remnants, neutron stars, and black holes. They can map hot gas halos around galaxies. They can identify regions where gas is being heated by shocks or by radiation from massive stars. By combining all these different types of observations, astronomers can build up a complete picture of local group galaxies. Each type of observation reveals different aspects of the galaxies, and together they provide constraints on theories of galaxy formation and evolution. Understanding the local group is not just about making observations. It also requires sophisticated theoretical modeling and computer simulations. These simulations allow astronomers to test whether their theories of galaxy formation can actually produce galaxies like the ones we see. Modern cosmological simulations start with the initial conditions of the universe shortly after the Big Bang. These initial conditions are based on observations of the cosmic microwave background radiation, which show tiny fluctuations in the density of matter in the early universe. The simulations then evolve these initial conditions forward in time, following how the density fluctuations grow under the influence of gravity. They track the formation of the first dark matter halos, the accretion of gas into those halos, the cooling and collapse of gas to form stars, the feedback from those stars, and the mergers of halos to form larger structures. Running these simulations requires enormous computational resources. The largest simulations track billions of particles, each representing a clump of dark matter or gas. They follow the evolution of structures from the early universe to the present day, spanning over 13 billion years of cosmic time. Running one of these simulations can take months on a supercomputer with thousands of processors. The results are impressive. Modern simulations can reproduce many of the observed properties of galaxies, including their sizes, masses, star formation rates, and gas content. They can reproduce the large-scale structure of the universe, with galaxies organized into groups, clusters, and filaments separated by voids. But simulations are only as good as the physics they include. If important physical processes are left out or incorrectly modeled, the simulations will not match observations. One challenge is modeling star formation. Star formation happens on scales of light years or less, far smaller than the resolution of cosmological simulations, which typically have resolutions of hundreds or thousands of light years. So, star formation must be modeled using subgrid prescriptions, simple rules that approximate what happens on smaller scales based on the larger scale conditions. Another challenge is modeling feedback. When stars form, they emit radiation and stellar winds. When massive stars explode as supernovae, they release enormous amounts of energy. All of this energy affects the gas in the galaxy, heating it, blowing it around, and sometimes blowing it out of the galaxy entirely. Getting the feedback right is crucial. Too much feedback in the simulation produces galaxies that are too small and have too few stars. Too little feedback and the simulation produces galaxies that are too large and too massive. Different simulations use different approaches to modeling feedback. Some use thermal feedback, injecting energy into the gas as heat. Others use kinetic feedback, giving the gas a velocity kick. Some include radiation pressure, from massive stars. Others include energy injection from supermassive black holes. The fact that different approaches can produce different results highlights the uncertainties in our understanding of galaxy formation. We know feedback is important, but we do not yet fully understand all the details of how it works. Despite these challenges, simulations have been successful at reproducing many properties of the local group. They predict that a local group-like structure should contain 2 large galaxies and dozens of smaller satellites, which matches what we observe. They predict that the satellites should be dominated by dark matter, which also matches observations. But there are still some tensions between simulations and observations. The missing satellites problem is one. The core cusp problem is another. Some simulations produce satellite galaxies that are too dense in their centers compared to what observations suggest. Some produce satellites with too much star formation at late times compared to the observed satellites which stopped forming stars long ago. Resolving these tensions is an active area of research. It requires both better observations to precisely measure the properties of dwarf galaxies and better simulations to accurately model all the relevant physical processes. One promising direction is to run high-resolution simulations specifically tailored to the local group. Instead of simulating a random patch of the universe, these simulations start with initial conditions designed to produce a local group-like structure. This allows the simulations to achieve higher resolution and to follow the evolution of the local group in more detail. These targeted simulations can then make predictions about specific observables in the local group. For example, they can predict the number and distribution of tidal streams, the orbits of satellite galaxies, the distribution of dark matter, and the star formation histories of different galaxies. These predictions can then be compared to observations to test the simulations. Another approach is to use simulations to interpret observations. For example, if observations show that a particular dwarf galaxy has an unusual orbit or an unusual star formation history, simulations can be used to explore what might have caused those features. Was it a close encounter with another galaxy? Was it a change in the gas supply? Simulations can test these hypotheses. The local group is intimately connected to cosmology, the study of the universe as a whole. Understanding the local group helps us understand the broader universe, and understanding cosmology helps us understand the local group. The local group formed from quantum fluctuations in the very early universe. In the first fraction of a second after the Big Bang, tiny quantum fluctuations were stretched to cosmic scales by a period of rapid expansion called inflation. These fluctuations became the seeds for all structure in the universe. Regions that were slightly denser than average attracted more matter and grew denser over time. Regions that were slightly less dense than average became voids. Over billions of years, the dense regions collapsed under gravity to form galaxies, galaxy groups, galaxy clusters, and superclusters. The local group is one of the structures that formed from these primordial fluctuations. Its mass, size, and environment are determined by the initial conditions set in the early universe and by the laws of physics that govern how matter behaves. By studying the local group in detail, we can test our theories of cosmology. For example, the number of satellite galaxies around the Milky Way depends on the nature of dark matter. If dark matter consists of WIMPs, we expect a certain number of satellites. If dark matter consists of axions, we might expect a different number. By counting satellites and comparing to predictions, we can constrain the nature of dark matter. The orbits of satellite galaxies also provide information about cosmology. The satellites are falling toward the Milky Way under gravity, and their orbits depend on the distribution of dark matter in the Milky Way's halo. By measuring satellite orbits and comparing to simulations, we can constrain the shape and density profile of the dark matter halo, which in turn constrains models of dark matter. The star formation histories of local group galaxies are also connected to cosmology. The timing of reionization, the properties of the first stars, and the growth of structure in the early universe all affect when and how galaxies formed their stars. By reconstructing star formation histories, we can learn about these early cosmic processes. The local group also provides a check on cosmological measurements made using other techniques. For example, one way to measure the expansion rate of the universe is to observe distant supernovae. Another way is to measure the cosmic microwave background radiation. These two methods currently give slightly different results, a discrepancy that cosmologists are working to understand. The local group can help resolve this discrepancy by providing an independent measurement of the expansion rate. This uses what is called the distance ladder. Astronomers measure distances to nearby stars using parallax. They use those stars to calibrate Cepheid variables. They use Cepheids to measure distances to local group galaxies. They use local group galaxies to calibrate Type 1a supernovae. And they use Type 1a supernovae to measure distances to distant galaxies and determine the expansion rate of the universe. Any errors in the early rungs of this ladder propagate to later rungs, so it is crucial to get the local group distances right. This is why so much effort goes into measuring precise distances to local group galaxies using Cepheids, RR Lyrae stars, and other techniques. One of the most exciting frontiers in local group research is the search for dark matter particles. We know dark matter exists. We can see its gravitational effects throughout the universe, but we do not know what it is made of. One possibility is that dark matter consists of particles that interact very weakly with normal matter. These particles would be all around us, passing through the Earth and through our bodies all the time, but almost never interacting with anything. Detecting such particles requires extremely sensitive detectors placed deep underground to shield them from cosmic rays and other sources of background noise. These experiments look for the rare occasions when a dark matter particle collides with an atomic nucleus in the detector. So far, despite decades of searching, no definitive detection of dark matter particles has been made. But the search continues, with increasingly sensitive detectors and new search strategies. An alternative approach is to look for the products of dark matter particle annihilations. If dark matter particles occasionally collide with each other and annihilate, they should produce detectable radiation. Gamma rays are a particularly promising signature because they travel in straight lines and can be traced back to their source. This is where the local group comes in. The dwarf spheroidal galaxies are ideal targets for this search because they are dominated by dark matter. If dark matter particles annihilate, the rate of annihilation should be highest in regions where the dark matter density is highest. The centers of dwarf spheroidals have very high dark matter densities, so they should be bright sources of gamma rays if dark matter annihilates. Gamma ray telescopes, like the Fermi Gamma Ray Space Telescope, have observed many local group dwarf galaxies, searching for this signal. They have found some excess emission in some directions, but nothing that can be definitively attributed to dark matter annihilation. The search continues with more sensitive instruments and more sophisticated analysis techniques. Another approach is to look for neutrinos from dark matter annihilation. Neutrinos are ghost-like particles that interact even more weakly than dark matter particles themselves. But neutrino detectors can observe large volumes of matter, increasing the chances of detecting a rare neutrino interaction. Neutrino telescopes like IceCube, located at the South Pole, have searched for neutrinos coming from the direction of local group dwarf galaxies. Again, no definitive signal has been found, but the searches continue to improve. The lack of a detection so far does not mean dark matter does not exist. It means either that dark matter does not annihilate at a detectable rate, or that we have not yet built sensitive enough detectors, or that we are searching in the wrong places or in the wrong way. Understanding the distribution of dark matter in local group galaxies is crucial for these searches. If the dark matter is distributed differently than we think, the expected signal would be different. This is why so much effort goes into measuring dark matter distributions using stellar kinematics and other techniques. Despite all we have learned about the local group, many questions remain unanswered. These questions will drive research for decades to come. First, how many members does the local group actually have? We know of approximately 50 to 60 confirmed members, but simulations predict there should be more. How many ultra-faint dwarfs are still waiting to be discovered? Are there satellites lurking behind the Milky Way's disk, hidden from view by dust and stars? Are there isolated galaxies at the edge of the local group that we have not yet found? Future surveys, particularly those using the Vera C. Rubin Observatory, will likely discover more members. Each new discovery will add to our understanding of galaxy formation and the nature of dark matter. Second, what is the exact nature of dark matter? The local group provides some of the best constraints on dark matter properties, but we still do not know what dark matter is made of. Future observations of dwarf galaxies, combined with direct detection experiments and searches for annihilation signals, might finally solve this mystery. Third, what shut down star formation in dwarf spheroidal galaxies? We have theories, environmental effects, supernova feedback, reionization, but we do not know which mechanism was most important or how they work together. Better observations of gas content and star formation histories, combined with improved simulations, will help answer this question. Fourth, what will happen when the Milky Way and Andromeda merge? Will the merger definitely happen, or is there a chance they will miss each other? If they do merge, what will the resulting galaxy look like? How will the merger affect the satellite galaxies? What will happen to the solar system? Improved measurements of Andromeda's velocity, particularly its motion across the sky, will help answer these questions. Simulations of the merger will become more sophisticated as computational power increases. Fifth, is there life elsewhere in the local group? We have not found any evidence of it yet, but the search is just beginning. As telescopes improve and we start to characterize the atmospheres of exoplanets, we might detect biosignatures that would indicate the presence of life. The James Webb Space Telescope is already observing potentially habitable planets around nearby stars. Future telescopes, like the proposed Habitable Worlds Observatory, will be even more capable. If life exists on planets around stars in the Milky Way, we might find evidence of it within the next few decades. These are just some of the questions that remain. Each one represents an opportunity for discovery, a chance to learn something fundamentally new about the universe. And the local group, our cosmic neighborhood, is where we will find many of the answers. Beyond the science, beyond the technical details, there is a deeper reason why the local group matters. It matters because it is our home in the largest sense of that word. When we talk about home, We usually mean our house or our city or our country, but the local group is home on a much grander scale. It is the collection of galaxies that contains not just our planet, not just our solar system, not just our Milky Way, but our entire gravitationally bound cosmic neighborhood. Understanding the local group means understanding our origins. The atoms in our bodies were forged in stars in the Milky Way and in the dwarf galaxies that merged with the Milky Way. The iron in our blood, the calcium in our bones, the carbon in our DNA, all of it came from stars that lived and died in the local group. When a star explodes as a supernova, it scatters these elements into space, enriching the gas clouds from which new stars and planets form. The solar system formed from a cloud of gas and dust that had been enriched by countless previous generations of stars. We are, quite literally, made of stardust from local group galaxies. Understanding the local group also means understanding our future. The likely merger between the Milky Way and Andromeda will reshape our entire cosmic neighborhood. While the merger is billions of years away, long after the sun has died and the Earth has been destroyed, it is still part of the story of the local group, and therefore part of our story. There is also something profound about the fact that we can understand the local group at all. We are tiny beings on a small planet, and yet we can comprehend structures that span millions of light years. We can measure the masses of galaxies billions of times more massive than our Sun. We can reconstruct the histories of galaxies that formed over 10 billion years ago. We can predict the future evolution of structures billions of years hence. This ability to understand the universe is one of the most remarkable things about being human. It required the evolution of intelligence over millions of years. It required the development of language, mathematics, and science over thousands of years. It required the construction of telescopes, computers, and spacecraft over hundreds of years. And it requires the dedication of thousands of astronomers working today, making observations, analyzing data, building theories. The study of the local group is a collective human endeavor built on the work of generations of astronomers, Edwin Hubble, who proved that Andromeda is a separate galaxy, Harlow Shapley, who discovered many of the first dwarf galaxies, Vera Rubin, whose observations of rotating galaxies provided strong evidence for dark matter, Fritz Zwicky, who first proposed that most of the mass in the universe is invisible, and thousands of others, famous and unknown, who have contributed to our understanding. This work continues today. Young graduate students are analyzing data from the latest surveys, searching for new ultra-faint dwarfs. Postdoctoral researchers are running simulations on supercomputers, testing theories of galaxy formation. Senior scientists are designing the next generation of telescopes that will allow us to see even farther and more clearly. All of this work is driven by curiosity, by the desire to understand our place in the universe. There is no immediate practical application to understanding dwarf spheroidal galaxies or measuring dark matter distributions. But there does not need to be. The pursuit of knowledge for its own sake is one of the noblest human endeavors. That said, the technologies developed for astronomy often find applications elsewhere. The CCD cameras developed for astronomical observations are now in every digital camera and smartphone. The image processing techniques developed for analyzing astronomical images are used in medical imaging. The algorithms developed for finding faint galaxies in sky surveys are being adapted for use in machine learning and artificial intelligence. But beyond the practical applications, there is intrinsic value in understanding the universe. It enriches our lives. It gives us perspective. It reminds us that we are part of something much larger than ourselves. When you look up at the night sky and know that you are seeing members of the local group, it changes how you think about that view. That faint smudge in Andromeda is not just a random patch of light. It is a galaxy containing 1 trillion stars, each potentially orbited by planets, some of which might harbor life. It is a galaxy that will collide with our own billions of years from now. It is a galaxy that formed from the same cosmic web that gave rise to the Milky Way. The Magellanic Clouds visible in the southern sky are not just pretty celestial objects. They are dwarf, irregular galaxies being torn apart by the Milky Way's gravity. They are cosmic laboratories where we can study star formation and galaxy interactions in action. Even the stars we cannot see, the ultra-faint dwarf galaxies invisible to the naked eye, matter. They are relics from the dawn of time, preserving information about the first billion years of cosmic history. They are dominated by dark matter, helping us understand this mysterious substance that makes up most of the universe. The local group is a reminder of scale. Our everyday concerns, as important as they are to us, take place against a backdrop of cosmic immensity. The local group spans 10 million light-years. It contains trillions upon trillions of stars. It has existed for over 13 billion years and will continue to exist and evolve for billions more. This scale can be humbling, but it can also be inspiring. Despite our tiny size, despite the brief moment we occupy in cosmic history, we can understand these vast structures. We can measure, analyze, and comprehend the local group. That is a remarkable achievement. The local group is also a reminder of our connection to the cosmos. We are not separate from the universe, looking in from outside. We are part of it. We are made of atoms that were created in the Big Bang and processed through stars. We live on a planet orbiting a star in a galaxy that is a member of the local group. We are cosmic citizens. This perspective can change how we think about ourselves and our place in the universe. It can make our problems seem smaller, but it can also make our existence seem more precious. We are here now, able to contemplate the universe. That is something special. The study of the local group also raises philosophical questions. If there are trillions of stars in the local group, and if many of those stars have planets, and if some of those planets are habitable, might there be other intelligent beings out there? Are we alone in the local group? Or are there others, looking up at their own night skies and wondering the same things we wonder? We do not know the answer to that question, but the mere fact that we can ask it, that we can seriously contemplate the possibility of other life in the universe, is profound. It changes how we think about life, about intelligence, about our uniqueness or lack thereof. If we ever do discover evidence of life elsewhere in the local group, it will be one of the most significant discoveries in human history. It will answer one of the oldest questions we have asked. It will tell us that life is not unique to Earth, that it can arise elsewhere, that the universe might be full of living worlds. But even if we never find life elsewhere, the search itself is valuable. It teaches us about ourselves, about what makes life possible, about the conditions necessary for habitability. It pushes our technology to new limits. It inspires wonder and curiosity. The local group is more than just a scientific topic. It is our context, our home, our connection to the cosmos. Understanding it means understanding ourselves. And that, ultimately, is why it matters. When we study the local group, we are studying our origins, our present, and our future. We are learning where we came from, where we are, and where we are going. We are placing ourselves in the largest possible context. Seeing ourselves as part of a structure that spans millions of light years and billions of years. That perspective is valuable. It reminds us of what we are, tiny beings on a small planet, but beings capable of understanding the cosmos. It reminds us of our place in the universe, one planet among billions, one star among hundreds of billions, one galaxy among dozens in our local neighborhood, one galaxy group among countless others in the observable universe. But it also reminds us that we are here, now, able to observe and understand. We live in a special time when the universe is observable, when we have the technology to study it, when we have the knowledge to comprehend it. We are fortunate to be able to contemplate the local group, to map its members, to trace its history, to predict its future. The local group is our cosmic neighborhood. Understanding it is one of the great scientific achievements of our time, and the quest to understand it fully continues, driving research, inspiring new observations, raising new questions. With each discovery, we learn more about where we came from, how we got here, and what the future might hold. This is the story of the local group, a story of structure and scale, of formation and evolution, of the interplay between matter visible and invisible, of galaxies great and small. It is a story written in starlight, across millions of light years and billions of years. And it is our story, because we are part of the local group, members of this cosmic community, residents of this vast neighborhood of galaxies. As we continue to explore the local group, as we discover new members and measure their properties, as we reconstruct their histories and predict their futures, we are writing the next chapters of this story. We are adding to human knowledge, piece by piece, observation by observation. We are fulfilling our potential as a species capable of understanding the cosmos. And in doing so, we are finding our place in the universe, not at the center, not unique, but part of something larger, something grander, something more wonderful than we ever imagined. That is the gift of understanding the local group. That is why we study it, and that is why it will continue to fascinate and inspire us for generations to come.